here's what's going to happen, right? So we have like, we want to build a very simple distributed database here, right? So I will, so we'll go basically step by step and build those like different companies that we will need separately. And I will first, for every, for every company and for every step of the way, I will go through a little bit of theoretical part, just, describing what we need to create, what those components would be responsible for, and these kind of things. And then for every of those steps, I will hand over to Dennis, and Dennis will do the coding under my guidance, I guess. And at the end, I will probably do some coding as well. We'll see how it goes. So, so first of all, since we're building a new system, let's talk about it, actual requirements first, right? We need to define what the requirements are and what the system has to do. And there are several things that we want to cover here. So first of all, we want to, we want to store data in memory, right? If you look at Apache Ignite or any other system, they are kind of focused on storing data in memory because it's very fast and it provides low latency and high throughput. And obviously, in our case, we also do this for simplicity. Like Ignite provides persistent storage. It allows you to store the data on disk as well with all the different configurations and different modes and all that. We will just, store the data in memory only for the sake of simplicity of implementation. The second one is the API. Again, we simplify it as much as possible. So we'll have just this very simple key value API, kind of hash map like API with just two methods, put and get. So we'll be able to update the data, providing keys and values, and we will be able to read those values by providing the keys. And we will also work only with string types. So just to avoid all those, serialization complexity for complex objects, we'll just store strings there. So that's just basic stuff. And then we, the system is distributed. So the reason why we want to distribute the system is to provide scalability, right? And this is the kind of the cornerstone of what we're doing here. And by scalability, I basically just mean that we want to have multiple server processes combined into a single cluster that essentially act as a single system, like with any distributed, database or any distributed system for that matter. And there are two major aspects there. The scalability is basically kind of twofold here, and that moves us to other two requirements. The first one is we want to scale out the throughput, the load, right? So we want to have multiple processes that are able to process different requests, right? So if we send, two updates in parallel or two reads in parallel, or many operations in parallel, we want those operations to go to different nodes so that they are processed in parallel as well by different servers, by different computers. And obviously this has to happen automatically, right? The system has to be able to figure out on its own where to send the request to make sure that data is available and everything goes right and data is consistent and all that. So we need this automatic request routing essentially. So when a client sends a request, the API should be abstracted from the fact that there are multiple nodes and the system chooses which node to send the request from. User should not think about it at all. It should just invoke get or put method and request should go where it needs to go. And the second aspect of scalability is distributing the data, right? So we can have a lot of data and we want this data to be stored on multiple servers as well, essentially to increase memory capacity, right? If we have, 3 servers, 10 gigabytes each, we can now store 30 gigabytes of data. And we can throw more nodes into the system to scale it out. And again, this has to happen automatically. Users should not worry about this. Users should just invoke put and get methods or other APIs, and the data should be stored on certain nodes. and should be distributed automatically and redistributed as well, if something changes, if we add more nodes or we remove nodes from topology. So these are basic requirements that we're going to have, and as I said, we will basically just go step by step, and for every of those requirements I will cover some theory, and I will also kind of build an architectural diagram as well, and we'll also do the same in the code as well.
And how is it related to Apache Ignite? Let me also share some thoughts on this, because, and why guys, you want to be on this live coding session. All their components that Val is going to explain you shortly also exist in Apache Ignite, and they are designed and they interact like some way. The implementation is only different. We are going to implement something simple because we have only 2 hours left. But our implementation, might be exactly how Ignite looked like when the founders of Ignite were writing the first code lines. What you will learn from this is that, in fact, like if you want to build something simple, scalable in memory on your local laptop, it's doable. All you need to do is just what are the primary components. But if you want to build the production grade system, you need to kind of invest like many years into the development. And that's actually what we are doing with Apache Ignite. So enjoy the process, learn what are the main components of Apache Ignite, and let's see how we can build the primitive implementation of an Apache Ignite cluster. Let's move on. Well, let's start building.
All right. So, so the first requirement, as I said, is the data storage and the API. I will actually cover, these are 2 requirements. I'll cover them together. So we have data storage in memory, and we have the API on the client side, that can access those that storage, which is somewhere located somewhere remotely on those server processes that we will set up. So let's build our architecture. So this blue box is our server process, right? So this will be a process that actually stores the data, and therefore it has the storage component, which in our case will be essentially, and you will see that in code, essentially just a simple hash map, concurrent hash map that can, store those key value pairs that we want to give access to the client. So that's our server process. Currently just has the storage. It's very simple. Since we access the server process remotely, we want to have certain communication layer, which will be responsible for all the networking, creating sockets and whatnot, and for all the serialization aspects of it. So essentially kind of creating a protocol for to communicate between a server process and a client process. And then we will have a client process, which typically, it will be your application. It can be a standalone application like a command line stuff. It can be a web application. It can be pretty much anything where you embed this client instance. And this client instance is essentially kind of a gateway and the API provider for the application. Obviously, it has to have the same communication layer because they need to, communicate with each other, and they need to know how to talk to each other and how to, how to read the data, how to update the data, and all that. So essentially, this is kind of a protocol for communication between the server and client, which is implemented in this communication layer, and the communication layer exists on both sides. And the API is just basically those 2 methods, put and get, right? And the application will go through the API, will invoke either put or get method on the API, and the API layer will use the communication layer to send those, particular requests to the server side, and the server side will respond back with the appropriate response. So that's just basically covers, so once we do that, and Dennis will just do that in the code in a second, we'll basically have a very simple key value database, but it's currently single node, right? So we'll start there. We'll just have a single node database with the server process, with the client process that are able to communicate with each other. So Dennis, I guess, hold on, I need to stop sharing. I think you can take over.
Let me take over the screen. And guys, those of you who are already using Ignite, so that to build connections between what Val is saying and what we are doing again, Ignite also has storage engine. It's not a primitive key value store, at least these days. It's more of a relational store, like powered by B+3 implementation that can persist data on disk and in memory. But it has a storage engine, right? Like every other database. At the same time, Ignite also has communication component. You usually configure communication by setting any parameters of the Ignite communication interface or other networking related interfaces. And I'll start, like as well suggested, we are going to start with the storage implementation. My first local database would be a basic key value store that keeps all the data in memory. And well, what can we use in Java like to do this really quick?
Yeah, just a little bit of context, right? So this is a project, which is mostly empty. It has some stubs. We have this, like internal API, which is not implemented yet, and we will implement it. Some of the code is commented out because it's just a boilerplate that we don't want to implement live. So it's, most of the code will do live. It's just kind of a skeleton for our project to make it a little bit simpler for us.
Yeah, I'll share the link in the chat window, because right now the project is not implemented, but by the end of this live coding session, the whole project will be ready and they will commit all the changes there so that you can go ahead fork it and use it on your own.
Yeah, so and we are starting with a storage component, right, as I mentioned. So that would be embedded in our server process. And therefore, this storage component should be able to, to store the data, obviously, in our key value format. So we can just use like a concurrent hash map here, which is, so we're using strings.
Yeah, and as you said, so right now we're making things simpler, right? We are just going to store strings. Keys and values would be of the string type, right?
Yep.
And storage is just concurrent, Java concurrent hash map that would take care of, let's say, all the synchronization aspects. If multiple clients are going to access my storage, and put it get, right? What could be simpler? We are just
that's trivial, right?
We are just asking this Java primitive. Yep.
Delegate to that map.
So this is I'm afraid that we got a problem with the link. Can you please change the GitHub link?
I think that I have to open it probably. I don't know.
Probably access stuff. If it's 404.
Let's do it later.
We can do this after. It's currently empty anyway. We'll commit the changes during the talk, and right after it, we'll figure out I think it's just private repo or something right now.
Yeah,
okay.
We'll do this. Just give us like 40 minutes. There will be a switch between me and Val, and I'll give access. All right, so that's our storage, guys, in memory, right? Nobody, I think, is going to argue. That's in memory key value store. We are just going to reuse GDK primitives concurrent hash map.
And that's an internal API, just to clarify, right? So that's not the API that the client will use or the application will use. This is our internal component which exposes those methods. I just wanted to clarify that.
Okay, now the communication, right? So now we need to implement communication because I want to run my server process, and I want the server process to be accessed from outside by my clients, which means that the server has to be able to open server socket connections, accept everything, and handle requests, right? What should I do here? How should tell me.
Yeah, so here we have three methods, right? So first, start and listen method, they will be used kind of on the server side. So start method should essentially create a socket, basically, a server socket, of course, so that it can accept connections. And then the listen method is the one, and you can see that it accepts storage. So that one would actually accept the client connections. And create workers for those client connections, and for every request that is coming, it will do something with the storage, right? So we can start with the start.
And this one used by servers, I'll just put some notes for those who are watching. And this one will be used by clients only, right? At least in our implementation. used by clients.
Yeah, execute method just sends a request that is provided here. It will establish a connection with the server side
and this one as well, right? Only by servers.
Yes,
I mean, because
correct.
in our implementation, it will look like more as a as how our thin clients in Ignite communicate. Thin clients usually do not accept any incoming connections. Thin clients instead always connect to your server nodes, and servers have a special port number open so that the thin client can connect. So that's like actually how our clients would look like. So let's do the server, right? As far as I remember, we decided we would, by default, every server will try to bind on port 4000, right?
Yeah, let's choose that as a default. It's obviously, arbitrary. Yeah, this is just our default number. In a real system, you will have this configured and all that. We'll just hard code.
And then we're opening this server socket.
Yeah, and one thing we need here is, since we will be starting several server nodes on the same box, you probably want to have like a loop where you will increment the port number and try to bind to the current one.
That's a good point. That's a good point. That's actually the same how it works in Ignite. I mean, like you can have multiple servers running on a single machine, even inside of a single Java virtual machine process. And here is we're also assuming that multiple servers will be running right on my machine. Surround with try catch. Okay, let's do this. And after that, it feels like I'm creating a simple networking application. I'm accepting.
No, you don't need to accept here. You will accept in the listen method. Here you just if you were able to bind, you just exit the loop and you want to save the server socket in a field. Yep.
All right.
That would work.
That's why I need you. Guide me. All right. And what's important, right? What can happen is that this port number is already used, and I just want to try to bind to list. I will increment this port number, and I will try to bind to it, to an additional one. That's actually, and once I successfully bind to any of the port numbers, I'm breaking this loop. And according to the contract of this method, I'm returning the port number this server process has bound to. Let's check.
Will be like we will use it going forward. It will become a little bit more clear why we have this kind of separate method that creates a server socket and why it returns the port number. For now, you can just ignore it. When we move on to the next section, it will be a little bit more clear.
And once my communication instance on one of the servers has successfully started, meaning that the server socket is waiting for incoming connection, we have to accept those connections. Let's move in here, right? Here is I'm using my server socket accept method. Once I've got any socket connection, meaning that a client application is connecting to me and wants to send any request. Now let's use the socket is open, and now I want to process the request. So let's do this.
Yeah, we can use just a simple, thread per client pattern, right? Which is probably will not be used in any real system, obviously for obvious reasons, but in our case, it's fine for simplicity. We're trying to simplify everything as much as possible.
So next, once the socket is open, I want to read a request from the client. And
so you want to have a loop here. You can create like object streams here based on what you have in the socket, and then have a loop that would use those streams.
Okay, we are going to use object output. Okay, we need to get an object input stream. Input, and we are creating this one from the socket input stream.
Yeah.
If any exception happens, let's just, try catch it. Also, let's quickly create a reverse stream, which is out, because once our server handles the request, we want to send a response. Object output stream, and again, we're just using socket. Once this is ready, eventually we need to read, right, the object.
Mm-hmm.
And here is, let's talk about the types of objects we're expecting to get from our clients.
Yeah, so there is this request package and the request interface, which is kind of implements our protocol in a sense. So we'll eventually have multiple implementations of this interface for different operations that we will have in our database. And this interface simply has this handle method which accepts the storage, so that whenever we get an instance of the request, we can invoke this method using the storage that is provided through the listen method as well. And the actual logic for the operation will be located in the implementation of this interface.
Oh yeah. Then we do this. We just getting this request. Oh no, what's that request? I just need request. This one. Request.
Just a question mark. Mm-hmm.
Okay, I think I need just to make this exception more generic. Once I receive it, I expecting that this request is to my storage instance. That's why I'm just letting the storage. No, I'm just using the logic. This request will be deserialized on the server side, and let this request to handle to do whatever it needs to do. I'm just passing in the storage instance of the server.
And the handle method could potentially return something if if there is something we want to bring back to the client side or to the requester side.
Yeah, for instance, for the get request, we're expecting to return something back, right? Yep. That's why result is here. All right, let's check. So we are opening.
Dennis, you also want to wrap this whole thing in a loop,
okay?
Because you can have multiple connections, obviously.
Yep. So that would be a blocking method. All right. So what happens once our server's socket is opened? We will be listening for incoming connection. Once any connection from the client arrives, we are processing that connection in a separate thread. Why do we have the while loop here? It's because once the first request is finished, the same client can send another request, etc., and we will be using the same socket connection. All right. So how about going ahead and starting our first server?
For that, we need to build it first, right? So if you go to the server class, yeah, this is basically kind of a container for all the components we need for our server process, and it will start right here. So at this point, we have storage and communication, so we can just add them as fields here, and then implement start method so that everything is tied up.
Okay, we have storage. Every server instance has its storage. It's supposed to keep a part of the data set. And also we have communication. And this in the start method, I think we don't need to initialize storage, right? It's just
storage is doesn't have any lifecycle stuff, but communication, you essentially have to invoke both start and listen methods one after another.
Okay, all right.
And we'll provide storage here, which we also created in the listen method.
Okay,
so
good.
This port number, yeah, we'll use. No, you provide the storage here.
Storage as well. Oh, it's greedy.
No, just the storage, yeah. So this storage instance, so that basically creates a link between the storage component and the communication component within the server process, right? So now communication component essentially knows about the storage instance we want to work with. And whenever communication will accept a request, get a request from a client side, it will use this storage instance that was provided here. And the port number, as I said, that was just returned, we will use going forward just in a minute. So it will.
Yeah, let's do
why
the
we
first
did that.
Right, let's do the first check. We have just implemented our server, we have storage, we have some basic communication implementation. Let me start my server process. I just want to ensure that that server is ready to, can actually bind to any port number, and meaning it will be able to accept connections. All right, the thing is compiles as always. Okay, we've got some, okay, that's the issue. I imported something by mistake. Let me restart. No any messages, no any logs. Let's fix this issue. Let me go back to the server and write something. Not actually here. Out server process started on and port number. And also, while I'm doing this, let me quickly do the same thing with their storage. Whenever anybody would be asking me to put any key, I would be just, let me write down some messages so that we can see that everything works as expected. Put request. And here is get request. Do you guys hear this noise? Should I shut down my window? Because there is some construction outside, as
Not
always.
too loud. I think
it's okay. It's not so loud.
Okay. Right, I added some debugging details. So right now, let's restart the server once again. Okay, it started. And actually, I can start another instance, right? Because I know that my communication implementation can already supports multiple servers. Yeah, this exception basically says that port number 400 is already 4000 is already busy, and the second server will be listening on this port. So I've got two servers running, but that's not the cluster yet, because those are just two disjointed processes. They're running on my laptop, but I cannot name this as a distributed database or storage or whatever. I need to join them together. And that's what we will be doing next when we will be implementing our Discovery SPI. But before that, okay, this test passed. Well, what's next? Let's implement client.
Yes, you also want to implement the client side. So for that, we need to execute the execute method, implement the execute method in the communication, and then implement the client itself.
All right, client. Right, yep, we are going to the communication.
Mm-hmm.
So here is generally the client is going to use just a plain socket connection to connect to any of the servers. We are doing this, new socket, new, no, I just need to use address, right? And just use address.
Now you need to separate
I need to
address, get address, and then port number.
Why don't they accept address?
So yeah, we obviously, this is not super optimal. We create a socket connection every time we want to send a request. Again, in a real system, of course, the socket connection will be maintained for the certain duration. And if you execute many requests one after another, the connection will be reused and all that. We're just doing some of this stuff again for simplicity of the implementation.
Do you remember if Ignite, for how long Ignite buffers? all those.
Well, I mean, yeah, if if you execute something constantly, if there is a client that just executes operations one after another, it will essentially exist for the whole duration of the as long as the client exists, essentially. There is an idle timeout that can be configured so that there's nothing is happening for a certain period of time. Based on that configuration, the connection will be closed. So yeah, it's kind of a generic pattern. But again, here we just for simplicity recreate the connection all the time, every time the request is sent.
And I guess I've finished. Let me see. Almost.
Yeah,
finished.
just need to cast it. Yeah, here we basically just do kind of a reverse of what we did in the listen method. We now write a request and then read the response.
Okay.
Yep.
The client basically, whenever any client application executes any put request method, the client implementation will call this communication execute method, open a socket connection to one of the ports, send the request to that server. A server process will handle it using this version of the implementation. So like that's actually where how the server is going to process all the requests that are coming from here. And then the server will respond. The server responds, and the client reads and returns to our application logic. Makes sense, I think, right?
Yep.
Okay, then what's next? Client, right? Final piece.
Yeah, so the client is our client process. It also has a start method for just some lifecycle, and it has our public API. So these put and get methods that we see here, these are the public APIs. So in the application, essentially would create an instance of a client, of this client class, invoke the start method to do some init work, and then it will be able to invoke put and get methods, within the business logic.
Yeah, let's for instance give you an example of how Ignite Thin Client implements. Ignite Thin Client is just an interface public API. It also has its version of the start method that accepts some of the parameters. And then once you get connected with that Thin Client to your Ignite cluster, the rest of the API provides you with key value put get methods. Thin Client also supports SQL, compute, etc. But our client, this primitive version, rudimentary version, supports just start, put, and get. So let's implement it, and then let's start our first application using this client API.
Dennis, I have a question. Does the C++ Thin client also support SQL statements? Or is it basically...
check this. I think that in the let's check what was released in the latest versions, because I know that the community expanded Thin Client API significantly, but I don't remember what was added to the C++. Unfortunately, not yet. Not yet. Are you using C++? Do you use C++?
I use C++, yes. I tried to start having a look at the C++ Thin Client API. I was struggling a little bit, but despite that, I think there's always the possibility just to use the standard ODBC driver and then access the Apache Ignite database via the ODBC driver. Is that possible?
Yeah, that's possible. Yeah, use this as a workaround for now. I mean,
yes.
And also send a message to our dev list, kind of trying to vote up for this enhancement, because you see that we have many more contributors to Java in .NET. That's why you can see that even compute APIs and like clustering APIs are already supported for .NET and Java. We just need to encourage our C++ contributors to at least to cover these gaps, because we have contributors.
Yeah, that would be nice to have that
Agree.
support. Yeah.
Okay. All right. Okay. Yeah, but as of now, yeah, use ODBC for SQL access.
Yeah. Thank you.
You're welcome. So next, then, so here as well, all I need to have is just communication, right? No any storage. Our client doesn't store any data. We have this communication class. And I don't need to implement the start method, right? because
Yeah,
the
not yet,
client,
because we will just use the execute method on the communication, which so we don't need to use the start or listen or anything else.
okay. And now it requests me, like, let's say when I want to implement the put method, I need to provide an instance of request. So let's implement request. We have put and get, right? So with put, all I need to do is I just need to implement this interface that you kindly created before. Let me do this put request. And I do implement request interface. So it returns something, right? It can return.
Put request, yeah, put request doesn't really return anything, so it can be just void and will return null from there. And the null will kind of act as an acknowledgement that, you know, operation happened, but we don't need to return anything meaningful.
And what we need for this put request is keys and values, right? Those will be serialized with this object, put request object. So I need to have keys, and we agreed that our rudimentary implementation would support the keys and values of the string type only, so that we can expedite our implementation. Value. All right, done. And here is, let me do this. What I'm doing, hell. No.
Yeah, just delegate to the storage and return null. Yep.
I just need to put key and value. And I'll explain you guys how this and return null, right? I don't need to return anything. So what happens when the client, my client application, will be sending an instance of this put request? The client has to pass, will receive from my application a particular key and value. This put request will be serialized by the Java's object output stream, and including the key and value object. Once this request is received by our server, the request object will be deserialized by the server, and the server will start executing this handle method. So how does it happen? Again, if you go back to the communication, you see that servers are listening for incoming connection. Once any connection from the client is opened, the server will deserialize this request, execute this handle method, and return something back to the client. And this handle method implementation is what exactly I've done. Like, I just want to take the storage instance of the server and put this key and this value on this server. That's it. And let's do the same for the get request. It should be even simpler. Okay, we implementing request, and we are returning strings only. We know that all the values are of the string type. Okay, as with put request, I need the application logic to provide me, to give me this key object. So that's what you as a developer, as the user of this database, has to give to the API. And next, when it comes to the storage method, we can do that like just this, right? Storage get key. All right, we've done it. We made it. Get request, put request. And if I'm jumping back to the client, eventually let's do this, right? We want to, here is, I have this like public API put. My client application asks me to put this key and value into my distributed storage. I'm creating this instance of the put request that is used internally by my database. In real life, like, this object is private, like it's not visible to your application code. And when it comes to the network, well, what do we do now? Because I need to give an address over.
Yeah, so we obviously, at this point, we don't know on the client side, we don't know the addresses of the server nodes, right? So we can, we will fix that going forward. For now, let's just hard code it with our default, which is localhost and the port which we've chosen, which is 4000, if I'm not mistaken.
Yep. Yeah, this will be improved. But in the meantime, my client, my first version of the client, always will be connecting to the server that is listening on this port. That's it. And let's do the same for the get method. Here is I'm doing get request key. That's it. Ready. And finally,
Okay.
let's suppose that let's do this. Let's use this client, right? I will create static void main method. And here is I want to test everything. Let me create the instance of the client. That's my public API. Just in case, I will call the start method that I think will be implemented by us later. Right now, the implementation is empty. And once I do this, let's do this. Let's say string key 1, string value, hello server. And all I do is I am.
You need the client as a variable.
That's true.
So that's essentially how how the application will look like, right? It will create the instance of the client, call the start method to start it and to initialize it, and then you have those APIs available, and you can invoke put and get methods or any other API methods that you might have there. The same you will do with the client, right? So you will create a client instance there. We provide certain, some static factories for convenience, of course, so that you don't have to create actual new instances. But basically, exactly the same happens. There is an instance, API instance that is created. It connects to the required server nodes and all that, and then you can use the APIs.
Mm-hmm. Okay, so I think that everything is ready for the test. Let me see if I have any servers running. Yep, I still have 2 servers running. Oh, no, this one is interrupted. I don't know why. Probably I shut it down. But I cannot shut down this one. Both are shut. Okay, I shut down both of them. Let me start the first one. I need only 1 server right now because anyway, my client is so primitive that it can connect only to one of the servers, and you have to provide what's the port number of the server. The server is up and running, and the next test is to start our first client. Okay, the client says that it received something back from the server. Actually, it put the key and value on the server and read this value back. If I go to the server side, I've got a lot of exceptions. That's probably because, let me see.
Yeah, Dennis, let's catch the end of file EOF exception here and just ignore it before you do the generic exception. Just another catch close for the end of file exception, and then you will.
And I'll just break,
do
right?
nothing. Yeah, you don't have to do anything here.
But like if I don't do anything, it will try to open.
Oh, I see. What do you mean?
But by the way, like
yeah, no, that's right, because it's inside the loop. Yeah, sure.
But like even like let's do this. Let's even simplify. If I get any exception, let me print the stack trace and break this loop. Let me close this.
I just don't want this to be printed out because the set of file exception will just pollute the logs.
I got it.
Because yeah, you can do the break there as well, but the point is that.
I got it. Okay. Yeah, we don't want the logs to be polluted. All right, let's restart client server. Okay, the client executed, and the server started on this port, and then the server said that someone requested it to put this record, and then someone requested to get this record back. So actually, everything is working, but we still do not have a distributed cluster. So the next task for us would be to have at least 2 servers running in such a way that they form a distributed storage or cluster or whatever.
Yep.
All right, Val, handing over the screen to you.
All right. Yes, I want to continue. All right, you should see the slides. All good?
Yes.
All right, yeah, so again, so we have those 5 requirements, right, that I've outlined in the beginning. So we basically have already covered the first 2. We have the storage and we have the API. Now, as Dennis said, we need to create a cluster. We need to make sure that we have multiple server processes that form a single system, a single cluster, that's basically what provides scalability to the system. So at first we will focus on the actual, on this actual process that will combine multiple server processes into a single cluster, right? And then we'll move on to our actual routing and all that. So let's say we have those 2 processes, right? We just run them typically on different computers, different servers. In our case, Dennis will run everything on a single machine, but generally speaking, you can have them, on different, running on different servers. So those 2 different processes, they essentially need to somehow know about each other, right? They need to know where they are located, on, their IP addresses, their port numbers. Typically, you will also need some metadata that they need to exchange with each other, like some configurations or some attributes and whatnot. And for all that, we will create a special company that we will call Discovery. So that would be the company that will be responsible exactly for that, for exchanging that meta information, basically, between the nodes. So there are different ways of how we can do this. Like Ignite, for example, basically implements kind of its own ring-based protocol. So all the information that needs to be exchanged across all the nodes, it kind of sent from one node to the next one until it completes the whole ring, right? So this is kind of a proprietary protocol that Ignite uses. One of the typical approaches for this kind of tasks is, and that's the one that we are going to use again for simplicity, is to have an external system, an external database, essentially, a highly available database that will store all that meta information and also notify all the different processes if something changes. Like in Java world, the typical example is Zookeeper, which is actually, that's what it does, right? And we could use Apache Zookeeper here. We will use actually the etcd database instead, which kind of does similar things, at least from our perspective, for our purpose, it can, they're basically the same. We're using etcd because it has a little bit simpler API. That's the only reason. We could use Zookeeper. We could use like console.io, for example, which also does the similar things. So what will happen is that every node that joins the cluster will register itself in this database. And the database will maintain the list of nodes that are currently in the cluster. And what all those databases like etcd, Zookeeper, and whatnot provide is basically kind of a watch or listener functionality, so that when something is updated, it will also notify all those different processes that participate and listen for updates. So what will happen is that, first node will join, it will register itself in the etcd, and then the second node will join. It will also register itself in the etcd, and then etcd will also notify the first node about the fact that the second node joined. And obviously the second node can read the information about the first one because it's already there. And this way they will kind of, as I said, know about each other and exchange all that necessary information to form a cluster. And now what we will do on the client side is basically the same thing, right? The only difference would be is that it will not register itself in the database because, we don't want other nodes to connect to the client node. But the client node needs to know about the server nodes, right? So it will, all the client will do is read the information initially, like basically the list of server nodes that are currently in the cluster, and also listen for updates as well, so that if there is a new server node joins, clients is aware of that. So that would basically, again, make sure that server nodes are aware of each other and essentially form a cluster. And it will also make sure that the client has all this information required to connect to the cluster. And we'll use that information going forward. So let's take a look at
Wolfgang is asking.
Yeah, we have a question in the chat. Well, Dennis, who can answer that? Do we use in Ignite something like heartbeat to notice breakdowns?
Yep, in Ignite, like Val is saying, Ignite's default implementation is homegrown, meaning that, like what Val was saying, a node to the left will be pinning or sending heartbeats to the node to the right. And like if the node to the right does not respond throughout the time of that heartbeat, like latency, etc., that node can be excluded from the cluster by its neighbor to the left. I can even show you the source code where this happens. That's the logic that does it.
Kind of a ring buffer.
I mean, it's kind of similar, I guess, to a certain extent. I mean, it's our proprietary protocol. It's not, we're not reusing anything there, but generally speaking, yeah, I mean, it's kind of a ring topology kind of a thing. Mm-hmm. And that's actually a good question, because that's what we're missing in our architecture, and we're not going to have that. So our implementation, again, for simplicity, will not detect failures. It will only like get the new ones. But yeah, of course, in the real system, you need to be able to detect that a node failed, which is much more, which is a much more complicated task. You need some kind of heartbeats or something else, so you know, some timeouts or whatnot. So yeah, we will not have this in our implementation, but any real system, and obviously Ignite will does have this kind of things.
Okay, thank you.
All right. Yeah, then let's proceed with the discovery. So right now I want to, the goal, like, just to summarize, I need to implement this discovery so that my server nodes form a single cluster. And then my client application just can connect to the cluster, and we will have a special routing protocol kind of implemented later. So, well, I think the discovery is already finished. Let's just, you know, like 1 minute explain to everybody what happens inside of this discovery.
Yeah, it's quite a bit of code here, so we decided to just pre-code it. And again, I will not dive deep into the etcd APIs, because basically that's what we use here. We connect to the etcd database. That's what happens on the line 42. So this client is etcd client, it's not our client. Mm-hmm. And then we essentially, we have to do 3 steps, right? So first of all, we'll just get, and we also have this topology map, which is line 39. That would be just the data structure that maintains the information about the nodes locally, right? And we will update it as necessary, right? So it will essentially, we assume that this map always contains the actual information about topology, which is essentially just a list of nodes. And the structure here is that we have UUID, which is kind of a unique ID for every node. We will generate it randomly for every node when it starts. We'll show it in a second. And the value here in this map is just the port number. So since we're running everything on the local host, we don't need anything else. Again, in the real system, you will at least also have an IP address and probably some other attributes as well. In our case, we just store a port number for every node. So as a first step, we will go to the database, to the etcd database, and get the list of nodes that are currently already in the topology. So this clunky code just gets the list. And for every key value pair, we will add this information into our map. So this add method, you can show the method. Yeah, it just parses the information and puts this into the topology map.
Yeah, so basically every type of process, let it be a server process or client process, they would have its own instance of this topology object that keeps that mapping, like what are the coordinates of the server, who has this port number. And that's why when any node joins so-called the cluster, it will populate this topology object from the etcd database that is running nearby,
Yep.
right?
Yep, so that's our first step, right? So we'll get like the initial list essentially. As a second step, what we'll do is we'll use this watch functionality, which is provided by etcd as well. So that would basically create kind of a listener, for the new update. So as I said, whenever a new node joins, we need to get a notification about that, right? So that's what it does. So for every whenever a new node joins, all the nodes that are currently running will get this notification, and we'll also add this information into the map. So that happens on the line 56, if I'm not mistaken. Yeah, so we also invoke this add method, which updates our map, and we'll also print out the full topology just for,
Yeah, let me also try to connect how this piece is related to the final step. Every server node has to register itself with etcd, and that's how it's done. Like every server provides the local ID, some identifier, and as every server is running and listening for incoming connection on some of the port numbers, once a server registers, it will do the put with these details into the etcd database, and all the other servers who are already listening, they would get this notification. etcd will report that, all right, there is some put happened, and we know that if this put happened, it means that a new server has joined the cluster. And we are not doing this for the clients, because our clients are not accepting any incoming connections. Our clients instead, they are initiating connections. That's why they don't need to register themselves with the discovery protocol. All right. So I think we can skip the rest, right?
So that's there is also this get topology method, which will just basically gets the list of nodes from that map. We'll use that going forward for some other stuff. So yeah, I guess unless are there any questions on that? I mean, if anything is unclear, we can clarify. But otherwise, I guess we can move on. Because yeah, as I said, this is just a little bit of boilerplate here, so we can. You just need to understand in general what's going on here.
Yeah.
So let's say again.
So what do I do next? So like I need to create this. Actually, discovery is implemented, and I need to use this logic on my server side.
Yes. So let's add this to the server.
Private discovery. New discovery instance.
And we want to use that in the start method. So the discovery has the join method. So all this logic that we've described is within the join method, right? Where we have to provide the local ID, which we need to also
generate something random.
Yep. So we provide this ID here into the join method, and we also provide the port number which the communication is bound to, right? So that I can again kind of creates this link. So discovery will so communication will bind into a certain port number, and discovery will register this port number in the database in the etcd, so that our other nodes know what port number to connect to, and the same goes to the client as well. So client also knows the port number this way.
Okay, let me go to, and also with the client, right? What should I do with the client?
Yeah, basically the same thing. The only thing, you don't need the ID, and we obviously don't have the port number because we don't accept connections here. So you just
I do this join. Let's just put now. Just to remind you once again, we still want the client to call this join method because we want client to subscribe to this notifications.
And
When a new
the
server joins the
current
cluster,
yep.
we want the client to update its own local topology. It wants to update its own version of the local topology because the client will be routing requests to one of the servers. But also, let's do this minor modification. This logic is executed if a server is joining, but if the client has joined, I just want to print out the current topology, right, on the client side. I just want to show how many servers are already in the cluster and the client is already aware of those. Actually, that's just, you know, system information. Okay,
right.
okay, well.
Do you wanna test it out? Just start a couple of servers in the client and see that everything is good.
So
and
I think that
you probably need to start the etcd database unless you.
Yeah, I will show the guys what happens. So right now you see that my server fails because it tries to connect. It's trying to connect to etcd, but etcd is not running. So let me start an etcd instance on my machine. I'm just going to use, you know, these instructions. I'm going to etcd and let me copy, this Docker command. I have Docker running, so hopefully everything will work fine. Okay, it's downloading everything from scratch. Okay, downloaded the latest version of etcd. Wonderful. This etcd thing is running on my laptop. So right now my server should be able to connect without any issues. All right, yeah, the server has connected, listening on this port number, and you can see that the server printed the current cluster topology. That's the only server we have in our cluster. And now the magic happens. If I start another server instance, that one will bind to this address. And right now I have two servers in my cluster. Finally, with the help of the discovery component, I eventually created a distributed cluster. Yeah, that's a primitive distributed cluster, but that's a distributed key value store running on my laptop. And we kind of, you know, took a shortcut by using etcd. In Ignite, again, and Ignite uses its own implementation of the discovery protocol. And with the client, right, if I want to start my client, let me start the client. Client starts, and clients also instantiates that instance of the discovery. Now the client sees that, all right, I've got two servers in my cluster. And the next step was, well, what should be? We need to
so client now knows about those two servers, but it still sends all the requests to the hard-coded port number, which is obviously wrong. So that's that's what we will fix as the next step.
Okay, I need to release the screen sharing, right? So you are about.
You can take it over.
No way.
All right. So that would be our requirement number 4, right? The automatic request routing. So again, client node currently knows about the server nodes that we have, but we currently, if we even take a look at our diagram, we have this discovery component on every single server and client, but it's not used in any way yet, right? And that's what we're going to do now. So essentially what we want to achieve here is that the API should use the information that we have in discovery to route requests to different nodes based on certain algorithm, based on certain mechanism. So essentially we will create this mapper component, which will exist within the client. And it will have a special method that will give us a node, address of the node based on the key that we want to update or read from our database, right? So we will first go to the mapper component, asking like, hey, tell us which node we should send a request to. And the mapper will then go to the discovery, use that get topology method that we have there, get the current list of nodes, do some magic there, and we'll talk about that magic in a second, and tell the API, tell the client which node to send request to, and then the API can go to the communication company providing that address. Yeah, so there is a guess about rendezvous hash maps. Actually, we are going to use that a little bit later. For now, we will just use a very simple hashing mechanism, but we definitely will use hashing for that. Obviously, again, there are different ways of doing that. You can do like range-based sharding. You can have like what Hadoop calls a name node, which kind of maintains these mappings. All those different approaches, they have advantages and disadvantages. We use hashing because it's kind of it's a very flexible approach, and it's very kind of generic, I would say, and Ignite uses that. So that's what we're trying to emulate here. But to start with, we will use a very simple hashing where we'll just execute a hash code method for the key object, and just get an actual node based on the size of the topology that we currently have. So yeah, let's. I guess it's better to just look at the code. Go ahead.
Just a quick question. Why do you use rendezvous hashing in Ignite? For instance, if I detect that a node has to leave the cluster, I could just shift all of the data to other servers with a simple mod operation as well.
I will answer that a little bit later.
Okay, sorry.
So what I've done, yes. So I think that that might take like 5 or 10 minutes, but I've just shared with you an article that was prepared by one of their grid gain architects and one of the veterans of Ignite community, where he explains visually like differences between various data distribution protocols. And then he kind of elaborates on how rendezvous hashing is implemented and why actually we selected it. That's a deep dive. It's like, a technical blog written by an architect and Ignite committer. So bookmark it and you can check it later.
That will also cover some of that, I guess, in the end of the presentation. But yeah, this probably goes a little bit deeper. Yeah. But anyway, you'll get an answer.
Okay, then. So what I should do now? I need to implement this mapper. Mapper. Yeah, that's the only one class that is not updated yet. So what do I do?
Yeah, so that's very straightforward, right? So that's exactly that node method that we have. So what you need is you need to have a discovery instance here, first of all, right? Because we will use that to get information about topology. We obviously, you don't want to create it here. Yeah, you will pass it from the server.
Okay.
And here in the node method, you can get the topology from discovery, which is the list, right? So we know how many nodes we have, and we can look up a certain node by index. We just need to find out the index based on hashing, right?
Okay, so now I'm doing this. I need to know the index of the nodes, right?
You can look at my background, by the way. It might help.
I don't see. Let me recall. It's like take this.
Yeah, we want to do ABS function, just basically to get rid of negative numbers, and then we'll do that for hash code and modulus on the size of topology.
Yeah, that's probably the simplest implementation possible, right? We just need to take the hash code and do this modular by the size. I think it's something quite similar how different hash maps are implemented in major programming languages. I guess so, if I'm not mistaken.
Yeah, that will give us, an index which is within the list, right? So if we have 3 nodes, it will be 0, 1, or 2, and you can just look up.
All right. Yep. Every node is given some index in here.
This get topology method, by the way, it's implemented in a way that it guarantees that the ordering is always the same. So if we invoke this kind of multiple times, it will always give us the same result, basically. It will not be reordered. So the same index will always be mapped to the same node. That's what it is.
All right. So right now, like with this mapper, whenever my client wants to put any record on the servers, this method will return me the server the client has to connect to, right? Exactly what's that server that owns.
Yeah.
This
So now you can update the client method, add the client class. Sorry, add the mapper there using the discovery that we already have, and finally replace those hard-coded values with the actual routing.
And here is all I do is I'm using mapper.
You don't need the new socket address here.
Seriously. That's right. That's right.
Yeah, so you just do. So it gives you the instance of a node class, which is kind of a descriptor, very basic. Yeah, that's right.
This way. All right. So right now my put and get method implementations are generic. Usually I'm asking the mapper instance to tell me what server owns this particular key. So whom should I connect to? And once the server is selected, we are just going to use our already created communication implementation to open a connection with that server and do all the rest of the tasks. Let's do the test, right? Let's update my client logic. Let's say my application. That's my. Let's assume that's my application, right? Application again starts the client, and right now, let's do this. Let's try to put and read back 10 random. I know 10 keys into the cluster, and then I will see, because even with this logic right now, the data will be distributed across my 2 server nodes. Even right now, we can support this scalability feature. All right, key, put value. Then I'm doing this. Okay. And just to avoid confusion, let's do it this way so that I'm incrementing. No, it's already will be incremented.
Yeah, it's already incremented, and also the put should be after.
Yeah, that's right. I'm doing put and then I'm doing read in the same loop. Okay, put and get.
Yep.
Let's start. I don't need to restart server because servers are do not use that mapper, but I need to start my client application. Okay, the client says that it's successfully connected and put and read back all those 10 records. Let's now check the logs of the servers. You can see that key 1, 3, 5, and 7, and 9 will map to the first server. And yeah, let's do it this way. That's what was sent to the first server, and keys 0, 2, 4, 6, 8 are distributed and put on the other server. So we've got our first cluster. It's like primitive database running. We have already created storage, communication, discovery, and the mapper that does all the routing. So, well, what's next? I think that's my part is over. I need to commit all those changes because you are going to do the final heavy lifting. Tell us, while I'm committing, just tell the guys what you're supposed.
Sure. Yeah. So as you can see, right, so we have, so as I said, we basically cover routing this way, right? So those different requests, they go to different nodes. Let me share the screen. Hold on just a sec.
Yeah, then I'm committing my changes while it's going to use the same implementation. And also, guys, I will while will be switching to the project on his side, as promised, I will open this source code for everybody.
Yep.
Okay, well, it's
So we covered the routing in the sense that different requests now go to different nodes. So as you have seen, we had like 10 updates and 10 reads or something, and 5 of those went to its first node, and others went to the second node. And to a certain extent, it actually covers the data distribution as well, because those different keys, they are now stored on different nodes, right? Because those 5 updates that went to the first node, they save the data on the first node as well. And the same goes to the second node. But the problem now is, imagine that you start another node as well, like a second node, like a third node into topology, right? This node is empty. It started empty without any data. And that creates an issue because data is not even distributed anymore. If you send something, and even worse, if you send a GET request to the third node, right? Because it's now mapped to the third node because the mapping has changed. And it was previously saved on some other node, you don't have it there. So it's not only kind of breaks the consistency, it also creates data inconsistency as well. Breaks the scalability, sorry. It also creates the data inconsistency. So that's what we're going to solve here, and that's what kind of covered in this last requirement, which is automatic data distribution. As I mentioned before, we not only want to distribute the data automatically, we also want to redistribute data automatically if something changes, if topology changes, if we add more nodes into topology, or if nodes are removed. As I said, since we do not detect failures right now, we are not going to cover the latter, but we want to cover the scenario when new node joins. And that's what we call data rebalancing usually. That's exactly the process I've just described. Whenever topology changes, the data is redistributed across the nodes based on that new topology, and that's what we call data rebalancing. So in order to achieve data rebalancing, we actually, if you think about it, we have all the information we need, right? So all the nodes, they have the discovery component, and they know about the nodes within the topology. So essentially, whenever something changes, and they also get those notifications about changes. So whenever something changes, they can react to it somehow and do the data distribution. The only thing we are actually missing is, so the general algorithm would be that discovery will notify the storage, right? Whenever something changes, the discovery will get a notification from the etcd, and then it will notify the storage, telling the storage like, hey, there is a new node, for example. So we need to do something. You probably should check if you should redistribute your data, rebalance your data. So here's the information about the new topology. So the storage then will go to the mapper that we have to add. So we'll have the same mapper component on the server side as well now, because we need to figure out those mappings in order to know which data we want to rebalance and which data we want to keep. So essentially for every key that we have, right, in the storage, we can check whether this key should be kept locally or should be sent to some other node, and we'll figure out to which node we have to send it. And mapper will, as usual, use the get topology method from the discovery. It obviously works in the same way. And then, whenever storage detects that there are some data that needs to be rebalanced, and could use the communication component to actually send the data across the nodes. So this red arrow represents the actual rebalancing process, the actual data reshuffle. So the only issue here is what should storage actually do to figure out which data needs to be sent to some other node, right? If you think about it, currently our storage stores all the data as a single hash map, which essentially means that whenever there is a topology change, it will have to go through all the keys, through every single key, and to check every single key with the mapper, right? Which is obviously not efficient. We have more data, now we have more keys to verify, and it's a linear complexity that we want to avoid, right? So first, before we actually implement the rebalancing, as a first step, we want to introduce data partitioning. Data partitioning has kind of multiple purposes, but that's definitely one of them, and probably like the most important one. Since we don't want to check the arbitrary number of keys, what we will do is we will create a constant number, a constant set of partitions. So let's say we want to have 10 partitions of data, and partitions are kind of buckets, and they will contain actual keys. And whenever we do rebalancing, we will be able to, we will only need to check those 10 partitions on whether we need to send those partitions to other nodes as well. And we don't care whether those partitions have any keys. They can be empty, or they can have millions of keys. We don't really care. We pick a certain partition, we check with the mapper whether this partition as a whole needs to be moved to some other node. And if we do need to do that, we send the whole partition to the other node. So that changes the actual mapper implementation a little bit, obviously. So it kind of creates this two-step process of mapping. So currently we do the hashing just based on the key, right? So we get the hash code from the key, and then we just apply it to the size of topology. So what we'll do here is we will have a two-step process instead. We will first map key to the partition, where we'll actually do exactly the same thing as we've done before. We will get the hash code and we'll apply the modulus function, but now we'll apply it to number of partitions instead of number of nodes. And what's important here is that number of partitions never changes, unlike the number of nodes. So if number of nodes changes, in our current implementation, the mapping also changes, and that's what actually causes the issue, right? With the constant number of partitions, this mapping never changes. A certain key is always, if there is a key that is mapped to partition number 4, for example, it will always be mapped to the partition number 4, regardless of how many nodes we have currently in topology, regardless of how many keys we have, how much data we have, doesn't matter. This mapping never changes. It is consistent. And then we have the partition to node mapping, which currently we will keep simple. We will also use this modulus function, and that will change going forward. But anyway, this mapping, again, this mapping is dynamic, right? So the mapping of partitions to nodes is dynamic, but this is fine because now we can check only partitions for whether we need to move them, right? So what it means is that we have certain keys grouped into partitions, right? And those partitions, from the rebalancing standpoint, they act as a whole, because that's the only thing that changes. Only the second step of this mapping changes when we add a node, for example, right? The grouping of those keys within partitions is constant, which means that we can, just go through all those 10 partitions and say, okay, if certain partitions need to be moved to some other nodes, we will send them, as a whole.
And if to relate this to Ignite, I think it's fair to say that the first part of this transformation, when you're transforming key to the partition, that's exactly what we do in Ignite, right? It's like the same operation.
I have a question.
Sure. Mm-hmm.
What happens if the number of nodes is larger than the number of partitions? And how does Ignite cope with that?
Well, it actually does not. I mean, generally speaking, you will, by default, we have here I have just 10 partitions. In Ignite, by default, you have 1024. So for the vast majority of use cases, this is more than enough, and you will never get into this situation. If you expect to have larger topologies like hundreds of thousands of nodes, it's likely a good idea to increase the number of partitions in advance.
I can do that via the XML files, I assume.
Yeah, you can do that. It's part of configuration. The only thing you have to do this in advance because it's kind of a fundamental property of the whole thing that this number of partition is constant. So if there is an event when you need to change number of partitions, you will essentially have to kind of reload the data and stuff, which should happen very, very rarely, if not never,
Okay, thank you.
All right, so let's. Where's Dennis? Where's the code? Can you?
It's already in the repository, in my repository, and unfortunately I cannot make it visible, but public, sorry, because that's the fork of your private repository. So that's you who has to make your repository public. And after that, I think my fork will be visible to everybody. But let me give you just, direct coordinates. But I think that you checked out it before, just, pull the changes.
No, I found the link. It's fine. Yeah, I'll make it public after after the meeting. All right, let me do the sharing. Why can't I share the screen? This is so weird.
So you want me to get back to coding?
Anyway, no, that's fine. No, for some reason I can't share the whole screen. I'm not sure why.
No, because nobody wants to see what you have on your wallpaper.
I can only share the whole thing. Anyway, so I'm currently checking out the project. Give me just a second. So I do git clone of that. Okay, and I will then open it in IntelliJ, and then I'll share the screen.
So do you think we will finish our implementation throughout the next 20 minutes?
I think so. Yeah, it should be fairly quick.
So that we at least have 10 minutes for the.
I had a quick question.
Sure.
We are using a bulk insert and a bulk query API on the client side. Not a single key value entry, but a bulk entry. We can insert a list of key value pairs in one go. In your mind, does that provide any specific advantages in terms of optimization of network bandwidth between the client and the server, as against doing a single key value entry, like in a for loop or something?
Yeah, so while is, I can take this question well. So that's definitely you will get a performance advantages, because when you're sending, let's say you have 10 keys and you have to put all those 10 keys into a cluster. If you're doing individual put requests, it would be, let's say, 10 round trips from your client to one of your servers. But if you're doing single put all of those 10 keys, the chances are high that, let's say, the first 5 keys will be sent as a single network message to one of the servers, and the rest keys will be sent as a single, let's say, message to the other server. So instead of 10 network round trips when you're doing individual put requests, you might have just 2 network round trips when you're using put all, if you have, let's say, 2 nodes cluster.
Understand. So so the max round trips would be the number of nodes essentially.
Yep.
Okay. But are there any known issues related to bulk inserts or bulk queries? I mean, we have observed issues related to JVM pauses and things like that. And we also read some of the latest 2.9 release notes that some performance and stability issues related issues have been fixed. So are they in any way related to bulk inserts or bulk reads? And the second question was about persistence. I do not know whether we intend to cover that in this session, but we have observed that with persistence enabled, we have kind of faced issues related to the persistent thread getting stuck and causing a cascading impact on the client. But once we disabled persistence, things were stable. So is persistence a recommended mode, or is it a proven mode in production in any of your use cases?
Yeah, when it comes to persistence, that's for sure production ready. It's being used by many companies, including large banks who, let's say, transfer money and store all the accounts and kind of money transfers in persistence. It might be, something, I think it will be hard for us to give you any specific guidance unless we see your stack traces, what exactly happens with that persistence. It might be, some other logic related issue, like let's say some deadlocks or whatever else that causes any troubles with your persistence. So with persistence, probably the best way would be to send a, if you have not done this yet, to send a question to the user list, and we can take it there because we need to see the logs. When it comes to the put all, check. Usually you might have troubles if, let's say, you are putting records into transactional tables or transactional caches. Like we have two modes, atomic and transaction, as you know. And let's say if you're doing several put alls from different clients, it might sometimes lead to deadlocks if the keys are not properly lined up or arranged. Again, let's, if you stay till the end, I think you'll have enough time probably at least to discuss in more details what's happening with your put all. And with persistence, it's better, to send the errors logs to the community user list.
Understood. Thanks.
Yeah, well, sure. All right. Well.
Yeah. So, so we want to implement rebalancing, right? So as I said, I mean, the general mechanism would be that discovery notifies the storage, and then, the storage will go through the data that it has, and we will have to introduce partitioning there to optimize that. And then we also need this communication part as well, so that the partitions can be sent over. So at first, as a first step, I will update the mapper, because as we discussed, the logic changes. We have this two-step process now. So I'll basically add two more methods here. So the first one, and those methods will actually implement those two steps. The first one will be the partition method, which gets the partition number based on key, and then the node method, which gets the node based on partition number now, not the key. I keep this method, which we had before. It will be, the implementation will be changed, but we still need it obviously on the client side, right? So first of all, and then there is the partition mapping, which I will also use for the actual rebalancing logic. It just gets the whole list kind of mapped to partition numbers. So first of all, we'll define the number of partitions, right? And as I said, this is a constant number, so we'll just have a constant. Let's say we have 10 partitions, and again, this never changes. It's just a static final field. So the partition method. Partition method is very simple, right? So we'll just do pretty much the same thing that we've done before. We'll get a hash code. Use the ABS to get only positive numbers and apply modulus, but now we'll use the partitions number. And again, like since this one is constant and hash code for a key obviously never changes because that's a property of the hash code, this function will always give you consistent results. So whenever you provide a key, you can call this function multiple times. It will always give you the same result. It doesn't depend on anything. Number of nodes, number of keys, doesn't matter. The result is always the same. And here we will basically do the same logic as we've done before in our previous method. The only difference would be that instead of using the key hash code, we'll use the partition number. But basically the logic is the same. We get topology from discovery. We look up the index for the partition and then look up the node. And the only thing left here is to re-implement this method because we don't need this logic here anymore. We can just essentially delegate to those two methods that we have. And we'll look up partition based on key and then node based on partition to have this two-step process implemented. So that's the mapper part. So now I will go to the storage, and in the storage we'll need a couple of things. So first of all, we need partitioning, right? So which means that instead of having like a single map of strings with all the data, we'll basically have map of maps, where in the upper map the key would be integer, which is the partition number, and the value would be another map which holds the data just for that partition, right? So we also need a mapper here, because we will use that to look up partition number based on a certain key in our put get operations. So we'll add the mapper field. And it will use, so we'll use discovery, we'll pass discovery here, and we'll create mapper based on that discovery instance. Mapper is created based on discovery, okay? All right, so now we can re-implement or update rather our put and get methods, which is fairly straightforward. We just need to, before we actually do an actual put or get operation, we need to look up that internal map from our storage based on partition, right? And to do the lookup, we need to ask the mapper which partition certain key belongs to, right? So we invoke this partition method that we've just added, providing the key. The partition method gives us the partition number. Then this storage.get method gives us the internal hash map for this partition, and we update that internal hash map using the put method. And the same goes to the get method in a similar manner, of course. So that's it for partitioning. Now let's implement the actual rebalancing. So the actual rebalancing logic I also have pre-coded because it's quite long. So what we'll do here is just uncomment the code. So it's kind of it's very basic logic. It just goes through. It gets this whole mapping from the using this partition mapping method. So as I said, it's just basically an array of which is the same size as the number of partitions that we have, and for every partition, it provides the node this partition is mapped to, essentially. So it's kind of a whole mapping of partitions to nodes. And then we go through every partition, getting the node for that partition, and then we check whether this node is local or not. And for that, we need a local ID field here as well, which we'll get from the server. So I'll create a field here. So that should be storage, just the wrong name. And so if it's local, we just create a new empty hash map for that partition. And if it's not local, we just move. We want to send that data. We remove it, and we want to send that data to the node this partition now belongs to. And for that, we first of all, we obviously need the communication component here. Again, I will create it as a field, and both local ID and communication I will pass here through constructor. And this will both of them will come from the server class where we have all those things. So if we have certain partition data for a partition locally, and but it currently belongs to other node, we want to send this through the communication. And for that, we need a new request implementation, which is called rebalance, which I will call rebalance request, and I will create it also under the request package. Okay. So here I get the partition number and the actual data for that partition, right? So that's what I need to send along with the request. So I will create the corresponding fields. And basically all is left is to actually implement the request interface here, which will do not return anything. And therefore I can just put void here, implement method. So I currently do not have any methods that would, update the map properly based on this rebalance request that is coming in. So let's say this method is called on whatever, on partition received, for example, right? And I will pass the partition and partition data here. And obviously all is left is to actually create the method in the storage class. And this is very straightforward. It just basically means that I've just got the whole, map for the certain partition. So I can just put it as is into my storage map. So I just do a put here. Partition number is my key, and partition data, which is the whole data set for that partition, is my value here. So that basically implements the actual rebalancing logic. The only thing that we are currently missing is the discovery part. So remember, like initially, discovery kind of has to notify the storage that this happens so that we can actually invoke this remap method. So for that, we'll add kind of a generic mechanism into the discovery, which, in our case, it will be used only for rebalancing, but generally speaking, it's kind of it's a typical approach to have this kind of thing. That discovery has a generic kind of a listener that would be invoked for every, or even multiple listeners, generally speaking, that would be invoked for every event that happens within discovery, right? And other components in the system can create their own listeners so that they are also notified when those topology changes happen. So this will be just a runnable in our case. So we'll just invoke it whenever topology changes. And we obviously have to do that within this listener logic, watch logic that we have here. So whenever we get a new event or new events, we first update the map, and then we notify other components through this listener. So only thing is left is to bring everything together, right? So first of all, currently we added the listener to our join method on discovery. And on the server side, we want the remap method on the storage to be invoked whenever topology changes. So essentially, basically, we'll just provide the, So we have the storage, and we'll provide the remap function link, function reference as this runnable. So this method will be, essentially invoked every time topology changes. And then we have also, we need to provide some stuff into the storage. I'll move it here so that I can actually do that. So I need discovery. I need my local ID, which is called my ID here, and the communication. So I think that's it. Oh yeah, the only thing is the client, because we added a listener, but we obviously don't need it here. So we just need to add null so that it compiles, and that's it. Nothing actually changes on the client substantially. All right, so boom, boom, boom. So if we go to, let me try this out. And to try this out, I will do the following. I want my partitions to be printed out. So if we go to, what's going on? Remap method, right? So after remapping is completed, like at this step, we actually kind of have my map is, up to date based on the new topology, based on the current topology that I currently have. So essentially, I can just print out the set of keys that I have, the set of partition numbers that I have, and it will show us which partitions are stored on certain nodes, right? So if so, that would be just a list of integers. It's a little bit slow here for some reason. So that would be my partitions. And then we'll just get the key set of, so this is, this is storage key set is just a set of partition numbers that are stored on this particular node. And I will, what's going on? I want to sort it so that it's a little bit better visualized. Okay, and I just print it out here. All right, so let's start a couple of nodes. We have a server. So for this particular test, I don't even need client, right? So what we want to achieve here is that whenever topology changes, the data is rebalanced, right? So what we expect is that when I have one node, it will have all 10 partitions, of course. And then, when I add a second node, some of those partitions will be moved to that second node. And obviously,
also,
same goes.
check the chat window. The guys suspect that you might get an null pointer exception. Probably you are missing something in this.
That's entirely possible. Will it result in NPE on the client side if a new server joins the topology? Yeah, you mean because the listener is, I guess you're right. But yeah, as I said, for this test, we don't really need clients. But yeah, technically, you're probably right. And I just need to, if listener is not null. Yeah, that's a good point. All right, so as I said, right, so we started the first server, and as expected, we have all those 10 partitions on this first node. Allow parallel run. Okay, I'll start the second one.
You know what? It takes longer on your machine to start everything.
I don't know, like everything is a little bit slow. I don't know why.
Are you watching Netflix in the background? Huh?
I wish.
So one question quickly on rebalancing.
Yeah. Mm-hmm.
What happens to queries on the keys for the partitions which are being rebalanced? Will they be served? Does the data remain on the original node while the data is in transit?
Yeah, that's a good question. So again, like our simplified systems does not really account for that. But yeah, obviously there's a whole lot of different race conditions there. Like you can, send a request during the rebalancing, and the question would be to which node to send the request to, and either to the previous node or like the new node and these kind of things. So yeah, the actual mechanism obviously will be much more complicated to consider all those different cases. Like what Ignite does, for example, is it basically maintains. So it first transfers the partition to the new node, and only after that it removes the partition on the previous node, like that's basically the reverse of what I'm doing here, because I remove and then send it out, so that for a certain period of time, there is no data for that partition at all. Ignite will obviously do different thing, right? It will send it first, and then it will evict it from the previous node. And in the meantime, this previous node can serve the request for that partition, and essentially you have kind of an additional backup in the meantime. And then there is, some specific mechanisms also. If this new partition gets a request for some of the keys that are not there yet because it's kind of partial partition. So as I said, there's a whole lot of different race conditions and different cases that we need to consider, which we kind of ignore here in this simple implementation. But generally speaking, yes, the system should definitely be able to handle all those different cases and make sure that the data is consistent.
And Ignite does this, not only for simple put get operations, but also for transactions. I think that our SQL engine also handles that, takes into account that the rebalancing can kick off at any point in time. So you're safe. You just don't need to worry about this. You just you do your part by building your application, and we'll do our part to ensure that Ignite handles everything consistently. And
sure. And second question related to backups. I'm aware it is not part of today's discussion. But if I create a backup node for the various partitions, so is backup an inline process to the put, or it's an offline process?
What do you mean by online, offline? Can you clarify?
So does backup happen in the same thread which does the put on the server, or it is written to another log from where the backups are created or replicated?
It actually depends on whether it's synchronous or asynchronous. So in Ignite, where you can have it either in primary sync mode or in full sync mode. And in full sync mode, I mean, technically all the network communication is kind of a asynchronous process, because we're using asynchronous IO, right?
Okay.
But from user perspective, what's important is that the backup updates can be either synchronous or asynchronous, depending on the configuration that you have on your cache. So if it's synchronous, that would mean that the client will wait for all the backups to be updated, and it will not get an acknowledgement before all the backups are updated. And in the primary sync mode, client will only wait for the primary node, and once primary node is updated, it will get the acknowledgement and can continue, and the backups will be then updated in background.
Okay.
So
one quick question, please. Yeah. So basically, we are having a Ignite cluster of 3 server nodes, and let's say there are multiple clients which are performing push and get operations over that cluster. So at a particular point of time, I mean, I can log into the Ignite visor and I can check the topology, and there it shows that okay, there are 3 servers, and at particular point of time, these many clients are connected to a particular server. So let's say now if at any point of time, one of the server nodes goes down, so what happens to the connected client nodes? I mean, let's say there are 3 applications which are connected to server node 1, and the server node 1 goes down. So what happens to the client application that are connected to? So is there any exception that is thrown that we should gracefully handle at our side, the client code? Or will it eventually lead into the client applications also getting killed?
That would depend on whether you use thin client or thick client. So thick client basically should be able to handle everything automatically, unless you have like a full disconnection from a cluster, right? If like the network of the client goes down, for example. In that case, you might need some special logic. There are reconnection exceptions, these kind of things. But unless that happens, and if we're talking about just a single node failure, then it will happen transparently for the client. With the thin client, I believe it might be a little bit more complicated, because there you basically you provide kind of a single IP address or maybe 2 or 3 IP addresses, and if none of those addresses that you provided are available, but there are still nodes in the cluster, then you might need that logic. But generally speaking, if you provide like 3 addresses, for example, you are covered for most cases because it will be a very rare event when 3 nodes go down at the same time.
Yeah. Okay. Just one more question in addition to this, basically. So in our Ignite server logs, basically we are seeing a continuous set of exceptions of different system threads getting blocked. Sometimes it's the checkpointing thread, sometimes it's the stripe related threads. So are there any pointers, I mean, in which direction we should, I mean, what kind of configuration should we check that may be causing these kind of deadlock like situations between the system threads?
Yeah, that's hard to tell without looking at the logs and all that. I mean, I guess the best option would be to write a message to the user list. Okay. Or to the Stack Overflow, and we have like the whole community of folks who will be happy to help you. Just provide the logs and all those error messages and all the information that you have, and they will analyze and help you.
Okay, sure. Thanks a lot.
All right, folks, let's finish this implementation. I think that we are already running out of time, but Val and I are ready to hang on for some extra time to take your questions. But let's finish.
Yeah, I mean, I'm done with the implementation of the rebalancing. So as you can see, right, so initially we had all the partitions on the first node, and now once I've added the second one, we initiated the rebalancing mechanism, and now the first node has only 5 partitions and other 5 partitions on the second node. So let me also add a third node, and I will show one more thing that we've got here. I'm not sure I will be able to cover that part in full, but we can probably just start and then you can take it over. So here's the thing, right? So I've added a third node here. So the third node got some of the partitions, right? It's partitions 2, 5, and 8, for example, right? In this case, which is a good thing. Obviously, we want this new node to get those partitions. But the problem is, let's see what happens with other partitions as well, right? So for example, if we look at, so what was that? 258, right? So if we look at this set of partitions that we've had before, so partition 2 went to that new node, right? And partition 8 also went to that new node. But here's the thing, we also had a partition 4 here, which is not on the new node, right? And it's not on this first node either, which means that it's currently on the second node, which we actually see here, which means that we have this data movements we not only move partitions to that new node that we've just added, we also move some of the partitions between those first 2 nodes that existed before. And partition 4, is an example here. Also, there is currently partition 3, and partition 9, those 2 were moved to the first node. So we moved partitions 3 and 9 from second node to the first node, and partition 4 from the first node to the second node. So if you think about this, these are completely redundant and unnecessary movements. They do not provide any value at all. And obviously they also consume resources and consume network and all that, because those partitions can be quite big. They can have multiple millions of keys or whatnot, and it will take time to send all this data across the network. And in the best case, you will get like significant degradation because of that. In the worst case, you will just saturate the network and make system unavailable for a certain period of time, or maybe even topology will break down. So this is kind of an issue that we have here, and that's actually what is solved by the rendezvous hashing mechanisms that we've mentioned before. So where is my? Oh, okay. So let me just maybe spend just a couple of minutes. Obviously, you know, it looks like we don't have time for the full, to go through the full section, but basically, you know, generally speaking, this rendezvous hashing algorithm is what solves this issue. So if we have a certain data set of like, what is it, 9 entries here. So let's say we build an app, right? And we have an information about accounts. And every record in our data set, you know, has a credit card number, some information about the owner and the balance, for example, right? And we want to distribute this data set across our data set. So if you use our algorithm that we're currently using, right, we map those keys based on just the number of nodes rather than, you know, and using this basic hashing mechanism, we'll get, you know, something like this, for example. So we map those keys to those nodes. Some of those keys get to partitions to the node 0.
You're not switching the slides. Well, you're not switching the slides. I just see let's code.
Really?
Yep.
Paused.
And while you are fixing this problem, just in case, guys, I will paste the link to a detailed article once again that explains how Rendezvous Hashing implemented in Ignite. You'll find it in the chat window in a moment.
Okay, I guess now it's okay. So yeah, so we just get some distribution, right? Meaning that, you know, some of the keys are on the first node, some of the keys on the second node, and some of the keys on the third node, and we'll get something like that, right? So we get some distribution. It doesn't really matter how it actually distributed. And if we add another node, so this index changes, the number of nodes changes, and therefore the mapping changes as well, obviously, right? And to a certain extent, that's what we expect, right? So we have like we have a couple of keys now on the new node, stored in the new node, which is a good thing, and that's how it will look like. So we have some other distribution, right? And again, if we compare those two things, just like I've done during my test, we have some of the keys moved to the new node, which is a good thing. But at the same time, we have this data movements which happen within the existing nodes. And that's a big issue, as I've described, right? That consumes a lot of resources, network, CPU, and whatnot. And this is something we want to avoid. And to avoid this, there is the mechanism called rendezvous hashing. Not the only one, though. There's also consistent hashing and actually some others. Ignite uses rendezvous hashing currently. That's why I cover it. And also, it's very easy to understand. The idea is that instead of calculating hash code based on a single key, we'll calculate hash codes based on pairs of the key ID and based on key node ID pair. And we'll do that for every node that we have in topology. So let's say if we have 3 nodes and we assign certain IDs, which just must be unique. In our case, we use UUIDs, but it can be anything for that matter. We'll get some hash values for those nodes, right? So for every node, we get different hash ID. And then we just use, sorry, I go quickly because we don't have enough time, but you can then follow up using that article that Dan's provided. But basically, yeah, we just we just find the maximum hash value among those 3, in case of 3 nodes. And that would tell us where to store that key, right? So in this case, for example, H2 is the maximum value. Therefore, that particular key will be stored on the node number 2. And then if we add another node, we'll do the same thing. We'll calculate this H4 for the node number 4. And what will happen, and that's where we come to the crux of the algorithm, is we only have two different outcomes out of this algorithm. This H4 can be either smaller than current maximum hash, or it can be larger than current maximum hash. Of course, assuming that we somehow cover the hash collisions, but that's kind of out of the scope of the protocol. It's usually is done outside and in some other way. So we just assume that we don't have collisions, and therefore there are only 2 outcomes. And if the H4 is less than maximum, the current maximum, then nothing changes because the current maximum stays the same. It's H2 in this case, and therefore this key or this partition stays on the node 2. If it's larger, then this new value becomes a new maximum value. And therefore it's moved to that new node, right? So we only have two outcomes. It's either moves to the new node that we've just added, or it's not moved at all. And that's exactly what we're looking for, right? So this kind of the algorithm itself guarantees that we don't have those redundant data movements within the nodes that currently exist in topology. And we get, the picture like this, right? So we only have keys or partitions moved to the new node, to the node number 4, but there are no reshuffle happening within the existing nodes. You can notice that the data distribution is not that perfect, right? We can kind of have 4 keys on the first node, for example, and only 1 key on the third node, and that's basically kind of that's a fundamental trade-off that we have here. So those two things, the evenness of the distribution and the efficiency of the rebalancing, they kind of conflict with each other, unfortunately. And that's what we have to deal with. We can optimize it using better hash functions or some other methods, but generally speaking, you should keep that in mind that you can have some data volume differences on different nodes because of that. In a real system, it's not that big because when we have a lot of data, it's kind of evens out more or less. But you should, again, keep this in mind and probably have some safe cushion for this kind of cases. So I think I will not go into implementation of that. I will implement that in the code and commit. It's actually very simple and it just does exactly what I've described. But not to take time, I think we can, if there are any questions left, we can go there. And yeah, that's basically covers all the requirements that that we have outlined at the beginning. So we have the data storage and memory. We have the API on the client side. They know how to communicate with each other, and we can scale out. We can add nodes, and the data will be rebalanced, and the request will be routed, and we basically have everything we want. So yeah, I'll finish the Rendezvous hashing implementation. I'll commit it into the code, and you can also check out the repository and play with it, and also made some changes,
And also like if you're curious, for curious minds, if you'd like to, you always can compare this naive implementation to the one Ignite has. So because like our implementation is straightforward, but Ignite also has the same components, and then just compare the complexity.